In this lesson, we're going to talk about continuity. The first thing that we need to do is understand the definition of continuity. So by definition, a function f is continuous at, specifically x equals c, if the following three conditions are satisfied. So this particular definition talks about continuity, specifically at a x value. The first piece of the definition is that the function value f of c is defined. That means there actually has to exist an ordered pair when you plug x is c into the function. The second qualification is that the limit as x approaches c of f of x exists. Notice that that's an overall limit. So with that part of the definition, it would be understood that you must have a limit from the left of c, and you must have a limit from the right of c for the overall limit as x approaches c to exist. And then the third qualification is the limit as x approaches c of f of x must actually equal to the function value f of c. So on here, I'm going to say layman's terms, continuity means that you can draw the graph without lifting your pencil. If you have to lift your pencil at any particular point in time, then that would mean that you have a point of discontinuity. So let's look at a graph to better understand this, and then we want to make sure that we keep in mind this particular definition along with the three pieces that make up your definition. All right, so on here it says use the graph to the right to answer the following questions. Is f of x continuous at x equals -1? Explain mathematically. What I mean by explain mathematically is to use the definition, and then if a piece or two or three is not met, then say so. So what I've done here to the side is I've basically numbered out the pieces. So in other words, number 1 says something about the function value at -1, and so we're going to go find the function value at -1. And then number 2, like I mentioned, we're looking for the overall limit as x approaches -1, so we're going to look at a left limit, a right limit, and then the overall. And then the third piece, we're basically going to make sure that the answers to the first and second pieces match. So let's go look at this. So the first question is, what's the function value of f of -1? So if we go over to our graph and we look at the graph, so we're looking specifically at -1 as the x value. So we're looking here. Looks like the function value at -1, there'd be an ordered pair there. So it looks like that actual function value is -1. All right, then we're going to look at a limit as x approaches -1 from the left. So if we approach -1 from the left, our function is down here. It looks like that function value is also approaching -1. So the left-hand limit is -1. Let's look at the right-hand limit as you approach 1. So the right-hand limit, you're approaching, -1. -1 from that direction, it looks like our function value is coming down to a point at that -1 value again. And so that would mean that the overall limit as x approaches -1 is also -1. So at this particular point, we look at this value here and this value here and see if those two are now matching. So essentially what we've said is we have the first two conditions met. F of c is defined, so f of -1 is defined and it actually equals -1. So the first part of our definition is met. The second part is that the limit as x approaches -1 must exist. Well, not only does it exist, but it also equals the function value at -1. And so that makes up our third qualification. And so there we're going to come down and say this particular one would be met because we can see that the limit as x approaches -1 of f of x is actually equal to the function value at -1, since these up here match. All right, so make sure on questions like this that you answer the question at the end. So the initial question was, is f of x continuous at x equals -1? Explain mathematically. So we've gone through and we've looked at each of the three pieces of the definition. And so on here we can say, so yes, f of x is continuous at x equals -1 since Number 1, f of -1 is defined. Number 2, the limit as x approaches -1 of f of x exists. Uh-oh, this thing keeps jumping around on me. And number 3, the limit as x approaches -1 of f of x actually equals the function value at -1. So all 3 pieces of that definition are met. All right, so let's look at another problem now. So same graph, but now we want to talk about continuity at x equals 1. So in this particular one, I've done the 3 bullet points over here to the side. So we're not going to rewrite those again like we did at the end of this particular one, but it says explain mathematically. So we're going to go and explore each of those options. So the first thing we want to do is look at the function value at 1. So let's go see if the function value at 1 exists. So we come over here to the graph. It looks like we do have a function value at 1. We look up here. I'm going to highlight this one so you can see it. That's actually the ordered pair. And so if we go across, it looks like the function value there would be 4. So it looks like f of 1 is equal to 4. So that part of our definition is met. The second part is that the limit needs to exist at 1. So we're going to say, let's take a look at the limit as x approaches 1 of f of x. All right, so coming over here, you want to approach 1 from both the left and the right. So if we approach it from the left, it looks like this is what my function values are getting close to. And if we approach it from the left, that's what my function values are getting close to. If I approach it from the right, that's what my function values are getting close to. So it looks like they're getting close to this open circle. The function value they're getting close to is 3. So that limit does exist. So we're good there. So the second part of my definition is met. So we'll check that off. And then on the third part of the definition says that the limit as x approaches 1 of f of x has got to equal f of 1. Well, we look here and we say, uh-oh, these 2 values here don't match. And so even though our first 2 pieces of the definition are satisfied, the last one is not. So on there, you could just put a slash through that equals. You could put an x here. And you could say, so no, f of x is not continuous at x equals 1. Okay, and then you could say since the limit as x approaches 1 of f of x is not equal to f of 1. So you give a justification for your answer and your work there. Okay, so from here, what I'd like to do is, also I'm going to warn you in the homework, you're going to go through some problems and they're going to ask you to tell why or why not. So which piece of the definition is met or not met. And so on there, I've tried to make sure that I've put the definition in the same order that the textbook gives, and then that way you guys have an easier time of answering those questions where it's asking, which piece of the definition is met or not met. All right, there's also a definition of continuity, not just at a single point, but specifically on an interval or a closed interval. And so on here, the definition of continuity on a closed interval is that it would be continuous on that closed interval if and only if it's continuous on the open interval, AB. That would specifically mean that for every single point, and that's going to be an infinite interval, but for every single point between A and B, there is continuity. And then to be continuous at the endpoints, you have to have continuity in a particular location. And what I'm going to do to explain this is just draw a little graph over here to the side. One of the graphs that we look at a lot for this has this particular behavior. So let's say for a minute this is A. We don't know what it is. And then over here somewhere is B. So notice there that between A and B, there's continuity. In other words, you can draw that graph without lifting your pencil. So that means that the function value exists for every point in there, the limit exists for every point in there, and the function value actually equals the limit for any point in there. So that's all good. And then for qualifications 2 and 3 in this definition, it says that if we're going to be continuous at the endpoints, first of all, you have to be continuous to the right at x equals a. Well, do you see here that a is our left endpoint, but to be continuous there, you'd need to be looking at a right type of continuity. So you're approaching from the right, and you see that we're continuous all the way down to that value. So we're going to be continuous from the right there. That's good. So that one's going to be met. And then for the right endpoint, you have to be continuous from the left of B. So as we approach B from the left-hand side, we can see that we have continuity there close. And so we would have continuity there at the endpoint. And so we would essentially be continuous on that closed interval from A to B. Don't get continuity and limits confused. A piece of continuity is limits, but limits and continuity are not the same thing. All right, this particular problem asks to give the largest interval over which this function is continuous. And notice here that I've given you the graph of the function as well as the actual function definition. On this graph, let me come in here and label. I'm not sure that you can clearly see this. This particular graph is understood to continuously go on to the right. So I'm going to put a little right arrow there on the end. And then this particular point, I think y'all can see that that's an understood close point. The thing I'm not sure you can see is that that value right there should be -5. Right, so this is basically a square root function. It's been shifted to the left 5 units. And so on here, notice that this particular graph is continuous all the way from this endpoint to the right, all the way to infinity. So the only issue would be, is it continuous at the -5? And so on there, looking at that, if we look at continuity from the right of the left endpoint, so going this direction, you can see it's continuous at all those points leading up to the -5. Because the -5 is included there, then we would actually have continuity at that point as well. And so on this one, we would say that this function is continuous on, we would use a bracket at -5 to include the -5. And then we would say to infinity, we always use a parenthesis around infinity since you can't actually include that value. So it would be continuous on that particular interval. I've also added here 2 notes, and please add this. You might want to put a little star there next to it because this is something that's important. A lot of times the textbook asks questions in 2 different ways. So they could ask you, what interval is it continuous on? You know, give that largest interval, which we've already done. But they can also ask the question of, where is f of x discontinuous? And so let me answer that question as well. Well, if we've already answered where is it continuous, then it's discontinuous everywhere else. So we can say, you know, from -5 on out that direction, it would be discontinuous. Because it's continuous at -5, we wouldn't want to include the -5. And so on here, we would say -infinity to -5. We'd use a parenthesis there to leave the -5 out. And then that's going to be the area where it's discontinuous. So be prepared either in homework, on quizzes, on exams to answer either one of those 2 questions. All right, here's a question, also graphing. It's always best to look at these kind of questions visually first so that we can get a good picture of what's going on before we go and answer these type of questions analytically. So on here, the first question asks, find all the values of x where the function is discontinuous. So we basically want to identify, number 1, where do function values maybe not exist at all? Or number 2, where do we not have limits? Or number 3, maybe the limit doesn't equal the function value. So we're wanting to look at those 3 things. And so on here, first of all, I do want you to be careful with the graph. Do you see there's a dotted line, vertical line going through, it looks like -1 here. That's a vertical asymptote. So you see up here at the top, it looks like the graph actually meets up there at the top, and you're going to have to understand that it doesn't because there's that vertical asymptote there. So the first thing is we don't even have the function existing at -1 because they're telling us there's an asymptote there. So if the function doesn't even exist, then we know for sure we have an x value where there's a discontinuity. So definitely at x equals -1. Now, there's a couple of other things that we consider. We're looking at places where maybe the limit doesn't exist. Well, over here, we see if we approach, let's say, -3 from the left, it looks like we're getting a y value that's negative down here. But then if we approach -3 from the right, it looks like we're getting a y value that's positive. So that limit is not going to exist at -3. So that would be another x value where we have a discontinuity. If the limit doesn't exist, then we're not going to have a continuous point there. And then the last one is over here at 2. Anytime you have a jump of some kind, so in other words, we have the function value defined at 2. It's this point down here. But you see it's a jump outside the function. So in other words, if we were graphing this, we'd have to lift up our pencil there to come down and plot the point down below. So we know we'd have a discontinuity there. The reason for that discontinuity, the function exists, so we're good there. The limit exists, so we're good there. It'll be whatever this value is. But you see the limit and the function value aren't actually the same thing. So that third part of the definition would be not satisfied there for the x is 2. So at x equals 2, we have a discontinuity as well. All right. This says, part B, give the largest interval over which the function is continuous. So now we've talked about discontinuities. Now we want to give a large interval, or the largest interval for which the function is continuous. So basically all you do is think about a number line, and anywhere you've said you have discontinuities, you're going to leave those values out. So obviously we're leaving out -1, and we want to make sure, I apologize, we want to make sure we do these in numerical order. So we're first leaving out -3 to the far left, then we're leaving out -1, and then we're leaving out 2. And so we want to now describe this in interval notation. So you're going to say that this is continuous on, and we're going to describe this interval. So -infinity, our first stop is -3. We're leaving that out with a parenthesis union. We start back up at -3, go to -1, leave that out, union. -1 to 2, leave that out, union 2 to infinity. So we see up here there are basically 1, 2, 3, 4 pieces to that number line, and we see that we have 4 pieces of our interval down below. So we're continuous on that open interval. Now in something like this, you don't have to worry about continuity from the left or to the from the right if your graph continues on. So in other words, over here, if this was the only piece of the graph, then it looks like we're actually going to be continuous at that endpoint. But because the graph then jumps and comes down here, then we don't have continuity at that right-hand piece, from the right there at -3. So unlike what we were looking at up here, where we were including that -5, you don't want to worry about including or not, including those if you have your graph continuing on. So down here, we wouldn't want to include the -3 right there because overall at -3, remember we said we have a discontinuity. Okay, let me know if you have any confusion there and I can clarify. All right, this particular problem says to graph the piecewise function and find the largest interval over which f of x is continuous. And I also want to add to your notes here, also find where f of x is discontinuous. And that way you're prepared to answer either question in your notes. So on this one, let's first start with graphing it. So a question like this, be careful to pay close attention to your instructions. So they want you to actually graph it. There's been things that we've done before where if it hadn't specified to graph, then you can maybe do things other ways, but that's actually a part of the instructions here. So there's a 2-part question. It wants you to graph and then find that largest interval over which it's continuous. All right, excuse me. So on here, let's work on the graphing first. So I'm going to come down here and we're going to label numbers 1, 2, and 3 so we can see those. And on here, for number 1, that's just a nice, pretty linear function. I'm going to write it as f of x equals. There's an understood slope of 1 on this one. It would be written as a 1/1 there in front of the x. And then we have the y-intercept of 1. That's good only if x is less than or equal to 0. So I'm going to come over to the side, and we're going to graph this. And if y'all need graph paper, you can definitely do that. I'm just going to freehand it. So we've got y-intercept of 1. Go ahead and put an ordered pair there. And on this one, notice it's for x less than or equal to 0. So here I'm good using a closed point at that location. All right, and then for slope, we're going to go up 1 to the right 1. Well, that's technically going in the wrong direction. I'd be going up and over this direction, and this is only good for x's less than or equal to 0. So technically I need to go the other way. So I'm actually going to come over here, and I'm going to put a negative with both the top and bottom ones. -1 divided by -1, still +1, but that would indicate to me that I would go down 1, left 1 to get to another point, and then down 1, left another to get to another. So we'd have these ordered pairs. So I'd have a graph looking something like this. So that takes care of the top one. Okay, for the middle piece, so part 2, we have a f of x equals x squared minus 1. So that's going to be a parabola-shaped graph. And so on that, what I'm actually going to do is I'm going to do a quick little t-chart, and I'm going to be careful about the x values I use. Notice here that it's only good for x's between 0 and 2, not including 0 and 2. Well, I'm going to go ahead and use 0 and 2 as x values in my t-chart, though, and I'm just going to make the note of, hey, they're going to be open circles at these particular points. So here's x. I'm going to start with 0, and I'm going to do 1, and I'm going to do 2, and then make the note, hey, here, these are going to be open. Okay, so plugging into the x squared minus 1, so 0 squared minus 1 is going to be -1, so that ordered pair is 0, -1. Here, I'm going to have 1 squared minus 1. Well, 1 squared is 1, 1 minus 1 is 0. Okay, so that's 1, 0. That one's going to be a closed point since it's in between. We'll go ahead and make that note if we want to. And then here, I'll do 2 squared minus 1. 2 squared is 4. 4 minus 1 is 3. And so 2, 3, that would be an open point. All right, so on here, I'm going to go up and graph these. So 0, -1 is going to be an open point. Use the orange again. So open here. And then 1, 0 is going to be closed. That would be in here somewhere. And then 2, 3 is going to be open. So up here. Now keep in mind that this is going to be a parabola-shaped graph. So I'm going to make sure not to do this with a straight line, but try to make sure folks can see that it's curved. All right, so that's parabola shaped. We're good there. And then now we're going to go on to the last piece. So number 3, that was f of x equals, and it was 1/2 x minus 2. But that's only good for x's 2 or larger. And so on this particular one, what we'll do is go through, and looks like we have a y-intercept of -2, and then we have a slope of 1/2. So what I'm going to do first is go down and catch this y-intercept. So there's the y-intercept. I'm not actually going to plot a point there, or if I do, I'm going to have to come back and erase it. Okay, so, and that may be what I do. I may come back and erase. But on here, if I plot that intercept, so there it is, then to get to another point, I'm going to go up 1 and to the right 2. I'm going to do this until I get to 2, and then I may continue on for a little bit. So on here, if I go up 1, right 2, that puts me there. Now, is that point included? Yes, because the x value for that point is actually x is 2, so we're good there. Now, if I do this one more time, then going from that point that I was just at up 1 and over 2, that's going to put me off over there. I think I need both of those 2 points for sure. I need this point as the reference because that's going to be where my graph is starting. And then I need the next one so that I can see that that straight line is going to go through there. And so I'm going to keep both of these 2 points and continue my line off there. And remember we started with that one, which was the y-intercept. I'm going to make sure that we erase that particular point so that we don't have something, I'm going to say, show up not being a function. And so there's our final graph. And I'm going to go ahead and color this in orange so that we can kind of see there that the orange is our graph. All right, now having the graph, it makes it easier to talk about continuity or discontinuities. So what I'm going to do here to actually answer the question, is I'm going to say where it's discontinuous first, and then I'm going to give the interval over which it is continuous. So we're going to say that this thing is discontinuous, and if you want to abbreviate, you can, at x equals. So we see to the left, there's a jump at x equals 0. So definitely x equals 0. All right, we also see there's a jump at x equals 2. Okay, so it's discontinuous at those places. Everywhere else is continuous. We have a nice smooth line. We wouldn't have to lift our pencil to graph it, but we're going to have to lift our pencil both at x is 0 and at x is 2. And so those are the only 2 points of discontinuity. So we've answered that question, discontinuous at those 2 x values, and then we're going to say it's continuous on, and we want the largest closed interval. So thinking about a picture, we're basically leaving 2 values out. And you guys don't have to draw this picture, it's just helpful. But on here, if we do that, the interval would be negative infinity to 0, and then union 0 to 2, and then union, so union 2 to infinity. And then that would be where this function is continuous. Okay, now I'm going to ease out of graphing and we're going to talk about continuity from a more analytical standpoint. So these questions says we're going to determine a continuity of a function. So find all the values of x where the function is discontinuous, if any, and then give the reason for the discontinuity. On this particular function, we want to think about our domains first, but we have to think beyond domains. And when we do that, I'll make sure to tell you all the information that you need to think about. So if I thought about domain first for this function, we've talked about in a prior lesson that the domain of a polynomial is all real numbers. And so we can see that this is a polynomial. It's just a sum or difference of nice, pretty integer, positive integer powers of x. And so it's a polynomial. So we're going to write that down. So part of this is just recognizing what the actual function is. All right, and then from there, we know that when we graph polynomials, because the domain is all real numbers, we'll go say that. Negative infinity to infinity, then that means that the function value is going to exist at every single real number value. It's also going to mean as long as nothing jumps around. So in other words, if you don't have a piecewise function, if you have a polynomial function, the polynomial functions don't jump around. So there's not going to be any breaks in the graph like we saw up here. So if there's no breaks in the graph, then that means we're good as far as limits are concerned. And then we call this basically a well-behaved function, meaning that the limit is going to equal to the function value. So if you want to, you can memorize that for polynomials, they're continuous anywhere. So you're going to say that there are no points of discontinuity okay. Since there's no points of discontinuity, we don't have to give a reason. And so on there, we would just say that. I'm going to go ahead and tell you where it is continuous. So if you were asked where this thing is continuous, you could say it's continuous on negative infinity to infinity. Okay, so you probably want to put that in your notes. All right, let's hop down to the next one. The next one is a rational function, and we've talked about rational functions. For rational functions, we've said that the domain is going to be all real numbers except for whatever value makes the denominator 0. And we can definitely see in this particular function that we're going to have a value that makes the denominator 0. However, with rational functions, we have to be careful because there are, when we graph them, places that there are holes possibly. And let me show you what happens here. If we went and we factored this function, which we wouldn't have to do if we're just talking about domain, but if we were to factor, we notice that the top is a difference of squares. Pull this up. So this is x plus 3 and x minus 3. And once again, emphasizing, if you're talking about domain, you don't want to do this because for domain, you're only interested in the denominator. But if we're thinking about the function as a whole, like if we're trying to go and we're trying to graph it, then we need to consider both the domain and then also this thing I've indicated, and that's going to be where the graph has a possible hole. And so on here, holes are going to occur in places where factors from the numerator and the denominator cancel. And so on this particular problem, we're actually going to have a hole at x equals whatever value would make that 0. And so x is 3 would be a place where you have a hole. So this thing is going to be discontinuous at x equals 3, specifically because of the hole there. Okay, and so if we're trying to clarify why it's not continuous there, we can say because f of 3 does not exist. And so on here, remember that originally we said in order for something to be continuous, the function value at that particular point has got to exist. Well, that doesn't happen on this particular one. And so on here, there's that part of your answer. And then also we can say that this thing would then be continuous on everything but 3, so negative infinity to 3, and then union 3 to infinity if they ask that question. All right, now on here, I'm going to also put a little note over here to the side because different things can happen. So put a little star, a little note. I'm going to go ahead and do a function where it's a little bit more interesting than this one. So let's say you have an x plus 1 and you have an x minus 2 on the top after you've factored. And then on the bottom of this one, you have an x plus 5 and you have an x minus 2. Okay, so this one, a little bit different from the last. We have a hole at where factors here would cancel. What's the 0 of that factor? The 0 of that factor is 2. So we would have a hole at x is 2, which would mean it's not continuous there. So in other words, f of 2 does not exist. Okay, and then also though, I'm going to number these, there's a vertical asymptote at whatever value makes this 0. So that would be at x equals negative 5. So once again, for that particular one, you could also say, hey, f of negative 5 does not exist. Okay, so I didn't want you to get the wrong impression that the only places you'd have discontinuity in rational functions would be at holes. There are two places you might have discontinuities. They're either at a hole if you have factors that cancel, or they're at a vertical asymptote if you have another factor that's left in the denominator that doesn't cancel, but still gives you a real number 0. All right, on this one, we're going to look at another piecewise function, but I'm going to look at this function analytically, meaning I'm not going to go and graph it like I did the other one. And this is going to help us with the last questions in this section as well. So if we look at this from a more analytical approach instead, so on here, think about each piece of your function. So if you've got piece number 1, piece number 2, and piece number 3. Look at those pieces individually first. So you've got an x plus 2. That's a nice linear function. It's polynomial. So it's continuous everywhere. The second piece, that's a continuous function because it's a constant function. It's also polynomial. Same thing with the bottom one. So all 3 of the pieces are continuous in themselves. So if that's the case, the only place that you may have a discontinuity is that the breaks, I'm going to say, brought about by forming the piecewise function. So the breaks in this situation would either be possibly at x equals 1 or possibly at x equals 2. So what you want to do is you want to make sure that the functions meet up at those possible breaks. So what I'm going to do is I'm going to say there's a possible discontinuity at x equals 1. To figure out if there actually is, what you do is you take the limit. We've talked about limits before of piecewise function. You do a left-hand limit and you do a right-hand limit. And so on here, if we do the limit as x approaches 1, Now, if we're looking at the top function, we want to approach 1 from the left-hand side because that's where that top function is defined. You remember on a piecewise function, we did something kind of like this to break it up. And we said, okay, if, here are the breaks, the idea, here's 1, here's 2, then piece number 1 is used to the left of 1, piece number 2 is used between 1 and 2, and then piece number 3 is used to the right of 2. So we can kind of see there. So if we're wanting to do, let's say, a left-hand limit, then we're going to be using the top function. Okay, we're using the top function, we're just going to plug 1 into that function to determine the limit. So we'll have 1 plus 2, and that's going to end up being 3. So the left-hand limit at x is 1 is 3. Let's now look at the right-hand limit. So the limit as x approaches 1 from the right-hand side of f of x. So now looking at it from the right, we'd be looking at using the middle function, the second one. We notice that middle function is just a constant 3, so that's 3. We notice, hey, those two match, which means the overall limit as x approaches 1 of f of x is 3. So on here, notice that the function value is defined at 1. The function value at 1, if we use the piecewise function, is 3. That's that constant function. The limit from the left and right of 1 exists, and the limit equals 3, which is the function value. Okay, so this thing is continuous at x equals 1. So we're going to say is continuous at x equals 1, since if we actually use the function and evaluate at 1, we'd be plugging into the middle function because that's where it's defined. That value would be 3. So there's the first part of our continuity definition satisfied. The second piece is that the limit as x approaches 1 of f of x exists, which we've said it does. And then the third piece is not only does it exist, but it actually equals the function value, which is true. Okay? So all three pieces of continuity are satisfied at x equals 1, so it actually is continuous there. All right, the other place that it might possibly be discontinuous is at x equals 2. So let's separate that out over here. So let's look now at possible discontinuity at x equals 2. Right? So on there, we want to look at the limit. So if we look at the limit as x approaches 2 from the left of f of x, we'd be in this location, so we'd be using the number 2 function, so that would be the function 3. Okay, and if we look at the limit as x approaches 2 from the right-hand side of f of x, that would mean we're using the function 3, so that we're plugging 2 into, so it would be negative 2 plus 1. Negative 2 plus 1 is negative 1. That's an issue because this and this actually don't match. And since those two don't match, then the limit as x approaches 2 of f of x does not exist. So we're going to say, so that didn't happen. And so we can draw the conclusion here that so f of x is discontinuous at x is equal to 2. Okay, let's go back on this one, make sure we've answered the question. On these, it wanted to know all the values of x where the function is discontinuous, if any, and then give the reasons for the discontinuity. On this one, we've said, hey, the limit doesn't exist, so it's discontinuous, so we're good with those two things to support our answer there. Now, on this particular one, if you wanted to give the interval where it's continuous, you could say this particular function is continuous on, and it's essentially continuous everywhere except for 2. So you'd say negative infinity to 2, leave that out, and then 2 to infinity if the problem asked for that. All right, now having explored this particular example analytically, that's going to help you with this last part of the lesson. So essentially here, they're going to give you some piecewise functions with some constants that you don't know, and they're wanting you to find the values of the constant so that it forces the function to be continuous. Well, that's easy, because on here, as long as the pieces of your piecewise function are continuous, then the only place that you might have a discontinuity is at the breaks. So in other words, on here, the break would be at 1. So the only place that you might have a discontinuity is at 1, because we notice that the top function is linear and the second function is quadratic. Those two are both polynomials which are continuous everywhere. That k value, that's a real number value that we don't know, but we want to force to make that k value such that these two graphs meet up. And so essentially all you do is on something like this, you set the two pieces equal to each other. So you say kx plus 3, the linear part, must meet the quadratic part, but specifically that has to happen at x is 1, the break that you're looking at up there. So since you know that x is going to be 1, on the next step down, you can substitute 1 anywhere there was an x, and then that will allow you then to solve for k. So you can do k times 1 plus 3, and then 1 squared plus 2 times k. Do be careful that you don't accidentally substitute 1 for k. K is the thing you're trying to look for. All right, and then from there, let's solve. So this is k plus 3. Over here, this is just 1 plus 2k. Just for ease, I'm going to bring my k's to the right-hand side. You can do whatever you'd like to there. So I'm going to have 3 equals 1 minus, and then 2k minus k is just going to be k. I'm going to subtract the 1 over. So we'd have 2 equals negative k. Divide out the negative 1. And so here, we'd end up with k equals negative 2. So negative 2 is the k value that makes this particular function continuous. The pieces are continuous everywhere, and then if I substitute the value negative 2 for k, that guarantees that the two functions are going to meet up and that this whole thing is going to be continuous. All right, the last one's a little bit more tricky just because it has 3 parts, but it's the same exact idea. So on here, we're going to do them a pair at a time. So in other words, for this to be continuous, those two have to meet up at 0. For these to be continuous, those two have to meet up at 0. So we're going to do just a 2-part problem as opposed to the 1 part that we just did. So number 1, we have to say that 1 plus x must equal k. So this function must equal that function at 0. So those must equal at x equals 0. That means I can substitute 0 in now for x. So 1 plus 0 must equal k. That means there that my k value must equal 1. Okay, so to make the top 2 pieces continuous, we notice all the pieces here are continuous because they're a linear function, make them polynomial. The top 2 are continuous and meet up specifically at k equals 1. And then number 2, looking at the bottom 2, so this piece number 1, this piece number 2, looking at the bottom 2 functions, the place that there might be a discontinuity is still at 0. And so we'd want to say, hey, k would have to equal 1 minus x at x equals 0. The only problem that we're possibly going to have here is that if the k values don't end up being the same for both 2 parts. If the k values aren't the same for both 2 parts, that's going to mean that there's a discontinuity. But if we solve here and we get the same k value for both parts, then that k value is going to create continuity for us. So here k would equal 1 minus 0. So k would equal 1 because these 2 things are the same. That means that we're able to use the same k value to make these functions meet up. Then we're good to go with k equals 1 as our solution. If you don't get the same thing, you would just say it's not possible to make this function continuous. All right, if you have any kind of questions, then definitely let me know. Shoot me email. Thank you.